Hello everybody, welcome to Unit 4, Lesson 1, where we're going to be covering Chapter 12, which talks about pointers. We have mentioned pointers in a previous lesson, but now we'll go into detail about the meaning of the pointer variable. By the end of this lesson, you should be able to declare and use pointer variables, use the address of operator to retrieve the address of a variable, and the dereference operator to dereference a pointer variable. And we'll talk more about what that means. You should also understand how pointer arithmetic can be beneficial, especially in the context of arrays. And speaking of arrays, you should also learn by the end of this lesson how to use dynamic arrays. And then finally, you should also know how to return a pointer from a function. Let's start by talking about what a pointer is. The main memory of a computer consists of many memory units. Each unit can hold 1 byte. Each byte is numbered sequentially, which is its memory address. Programmers of high-level languages such as Java and C++ typically don't need to mess directly with memory addresses. But it's critical to understand what's going on under the hood. High-level programmers do, however, manipulate variables, which are really just abstractions of memory units. A variable is a named location that can store a value of a particular type. When we declare an int variable, say in this instance sum, 4 consecutive bytes will be allocated from main memory to store this variable. The address of the first of those 4 bytes, in this case 900000000, will be recorded as the address of sum. Whatever you put into sum during execution will be stored in those 4 bytes. And currently, we've set sum to store the value of 25. So you can see here that it's storing the values of FF, which is hexadecimal for 25. Here we're using the big endian example because it's easier to follow. If I start swapping around this memory location and put FF here and the rest are followed by 0, it's a little bit harder to follow when you're not used to thinking about it in those terms. So your system probably uses a little endian setup, but we're going to use big endian just to make the examples easier to follow. A short type variable requires 2 bytes. Again, the address of the first of those 2 bytes, 900000004, will be recorded as the address of age. And those 2 bytes at this point store the value of 31, which of course you can see represented by the value hexadecimal 1F. Again, 1 is 16, F is 15, so 16 plus 15 is 31. And again, you can see that we're storing it in the little endian format. Similarly, a double type is going to require 8 bytes, and just like all the other examples, you can see that our memory address is going to be 9006, right? That's, or not 9006, excuse me, 9000006. It gets really tired saying that. And the value here is just some really big number, okay? Here's the value in decimal, and you can see the corresponding value in hexadecimal format. Now let's take a look at what we're doing when we create a pointer variable. So here's how we would create a pointer variable. In this case, we're creating an integer pointer called sum pointer, and we're setting it equal to the address of the sum variable, which, if you recall, is up here. Now, the pointer variable is going to occupy 4 bytes in memory because we use it to store a memory address. So here you can see the 4 bytes that sum is occupying. Its address is 900000003, right? And we've set its value equal to 9000000, which is the address of the sum variable. So you can see sum here, its address is this, and the corresponding address is here, right? I'll give you a little arrow to make that clear, okay? So we say that the pointer, sum pointer, is pointing to the address of sum. A pointer variable is a variable whose content is a memory address. A pointer indirectly references a variable because by visiting the address stored in a pointer, you can find that variable. A pointer variable doesn't hold the value you need, but rather the address of the variable which holds that value. So you might be asking yourself, okay, I get it. It's a variable that stores a memory address. But why would we want to use pointers in the first place? Well, remember pass by value and pass by reference parameters? For a pass by value parameter, a copy of the argument is sent to the function. Therefore, whatever you do in the function doesn't affect the original variable that you passed in. However, for a pass by reference parameter, it's actually its address being sent into the function. This allows us to access and modify the original variable. An address is often smaller than an object, and therefore it's faster and much more efficient to pass an address rather than to pass a copy of the value, because that's extra operations, and it might be a lot more memory that's taken up because we're having to copy maybe a large object. Now, you might remember reference variables in Java, that is any variable that points to an object. Well, it's really just actually a pointer behind the scenes. Java just doesn't refer to it as pointers. They refer to it as just reference variables. So the most common use of a pointer, though, is for dynamically allocated variables or arrays. And we'll spend a lot of time later in the lesson talking about those and how to use them. Now that you have a better understanding of what a pointer is, let's talk about how to use them. You may declare a pointer variable in any one of three equivalent styles. If you declare multiple pointer variables in one statement, remember to have an asterisk before each pointer variable, like that. So you can see here we have integer pointer 1 and integer pointer sum pointer. Okay, so this is critical that you put a asterisk before each variable. It is not enough to have int star p1 and then just some pointer without that. So as a convention though, when naming pointer variables, start with the letter P or end with ptr. So that way the user or whoever's reading your code knows that it's a pointer. And there are two operators that are used to work with pointers. The ampersand to get the address of a variable, and the asterisk to reach the variable pointed at by the pointer. Okay, so this is known as reference, and then this is the dereferencing. Okay, so they're opposite of each other. For example, given two int variables, t and u here, so we got integers t and u, ampersand t gives us the address of variable t, and then we can store that in the address pointed at p when we declare it as a pointer. So here we have pointer p, we're dereferencing p, so we can say whatever the variable is that p points at, we're going to be setting it equal to 20, right? So here p, we're assigning the address of t, so it goes out in memory and says, oh, it's pointing to this memory location here. Okay, p is equal to that memory location, but here we're saying we don't want the address of p, we want the variable that p points to. Okay, so this is called dereferencing. And when we dereference something, we can pass in an actual value. We can also modify a pointer to have it point to a different int variable. Since p is an int pointer, it can only point to an int. So that brings up the point, pun intended, that a pointer can only, let me get my laser pointer, this is critical, a pointer can only hold an address of the declared type. It cannot hold an address of a different type. Okay, so in this case, this is the same code we had in the previous slide. This is fine, but here we're declaring a variable f that's a double. We cannot assign p to point to the address of f. And again, keep in mind, we are not dereferencing p here. So we are assigning it an address. Here we are dereferencing p, so we can actually assign it a value. So make sure you realize the difference. So here we're getting the address of u and assigning it to the pointer p. Here we're getting a value, which is 20, and we are going to store that in the variable that p, or the memory location that p points to. All right, down here we're trying to assign p the memory location of f, but that's not going to compile because f points to a double and p only holds pointers for integers. One thing that I would like to clarify is pointers versus references. We'll talk more about it in depth later in the lesson, but I want to mention it real quick. When we're passing values by reference, you'll often see a function heading like this. Here, x is a reference, or an alias to another integer. It's a type, not a usage of the address of operator. Okay? So this is indicating that x is a reference. If we look at this program, our output would be like this. X is our value, and xref is the same value. If we change x or xref, we'll see the change in the other value. When we declare a reference variable like this, we do not need to use the address of operator to initialize the value. The compiler will do that automatically. And this is similar with pointers. Be aware of the difference between declaring a pointer type and dereferencing a pointer. Okay? So here you can see that we are declaring a pointer called xPointer, and we're giving it the address of x. Here we're declaring an integer, and we are assigning it the value of our xPointer that has been dereferenced. So this is kind of a bit confusing when you see references in function headings and you're declaring pointers, you know. So it's just something that I wanted to specify. Remember, when we are declaring a variable in a function header, we are declaring the type. So if you see this in a function header, you're saying I'm passing in a reference. If you see it on the right hand side of an assignment operator, you're using this as the address of operator. So just wanted to try to clarify that, and it's probably still confusing, but the more we use it, the more you'll get used to it and you'll get a better understanding of it. Now, going back to our memory diagram here, a pointer to an int, in theory, could also be used to hold an address of a double. However, in order to dereference a pointer, we must know how many bytes the variable points to occupies. If it's an int pointer, we need to access all 4 bytes starting from that address. Okay, so starting with this address, then we've got 4 bytes, right? If it's a double pointer, we need to be able to access all 8 bytes starting from that address. If we only access the first 4 bytes of a double variable, we wouldn't get a valid value. That's why a pointer of one type can only point to variables of that type. Now, C++ defines a 0 kind of value for pointer variables. A null pointer can be useful when we need to specify that a pointer points to nowhere. Before C++ 2011 standard, either a 0 or a constant null works. Null pointer can be assigned to and compared with a pointer variable of any type since C++ 11. So before C++ 11 we had to use 0 or null, and then since then we can use this null pointer type. However, a null pointer cannot be converted to an integer type value except for Boolean values. So here you can see we're declaring I equal to a null pointer, but we can declare a bool variable or boolean and set it equal to a null pointer because this is going to return true or false. And here's a segment of code to show that that null pointer value can be converted to a bool type. And here's the result of this segment of code. And we can tell by this that the null pointer evaluates to false, because here we've set our pointer equal to null pointer, right? And then we print out the value of it. And if p, print this, else print false. And so since p is null pointer, it evaluated to false, so we get the false evaluation. Okay, this right here is what the contents of p contains, which is all zeros. This can be very convenient for us to check if a pointer is null before we dereference it. So here's some example code. And here's the result of this code. You can see the first time we call check pointer, so we set x equal to 42, then we declare a pointer of integer type, and we set it equal to null, and we call check pointer, and we pass in the pointer, right? And so it says, hey, if pointer is true, do this thing, otherwise do this, right? Well, we set it equal to null pointer, and as we know from the previous slide, since a null pointer will evaluate to false, it's going to execute this part of the if statement, right? The false clause. So the second time we call it, after we assign it to the address of x, it's no longer null, so you can see that it's going to point to the dereference value and it's going to execute the true clause of the if statement. Okay, so that's how you can use the null pointer to check to see if your pointer's been validly assigned to a proper variable. Now that you have a better understanding of what a pointer is, we can take a look at pointer arithmetic. And this is kind of some pseudo black magic at first, but you'll get the hang of it later on. Let's take a look at this memory illustration again, and let's just focus on the int and the int pointer. We can perform some arithmetic on pointers, meaning we can increment, decrement, add, and subtract. If you increment an int pointer, it will advance 4 bytes to point to the next int in memory, regardless if there's a valid int there or not. Likewise, decrementing it will move the pointer back 4 bytes. If you increment a double pointer, it will advance 8 bytes. If you add 2 to this int pointer, it will advance by 2 ints, that is 4 bytes and another 4 bytes, so 8 bytes in total. And as you can see, this is right in the middle of the memory space where our double was being stored. Of course, if we subtract 2 from the pointer, it'll move it back to where we started. Now, in this situation, you might be thinking, well, it doesn't seem like pointer arithmetic is very useful. It just gets me into trouble by pointing me into memory blocks that I don't belong in. And I would be inclined to very much agree with you. So can you think of a situation where it might be useful? What if we had an array of ints? Now we could use pointer math to then navigate between the different memory locations. It helps to remember that an array is actually a const pointer, or a constant pointer, and stores the address of element 0. So if you assign an int array to an int pointer, that pointer will point to the first element in the array. Next, you can move this pointer to point to other elements in the array. Since an array is a constant pointer, we can't modify it to have it point to another location. We can only do this with pointers. If you recall from earlier lessons, we had an output statement like this. This statement will print E instead of me1, okay? Because you can see right here we're saying, hey, output this to the terminal. I want to do this text right here plus 1, and it's only going to print out E. This compiles, but it's not a string concatenation. Me right here is a C string, which is a character array. This C string plus 1 will retrieve the character at index 1, which is the letter E. Now if you had a longer word, the stream insertion operator would start at the letter index in the location and then continue printing until the null character was encountered. Like in this situation right here, we have the word funky, and so we're going to index it starting at U, and then it's going to print the rest of it until it encounters the null termination character. So it's just going to print out unky. Aside from arithmetic, we can also compare 2 pointers of the same type. Let's take a look at this example. Remember, a C string is an array of characters with a null character at the end. So here we can have pointer 1 point to the first character of this C string, and pointer 2 point to the last character in the C string. So here we're declaring a character array T, and we are going to assign T to the pointer. And remember that this is just a address of the first element in the array, so we can do this. Our second pointer is going to point to the last element of the array, which is the first element of the array, plus the size of the array minus 1. Okay? We then set up this while loop using these two pointers. If we don't return false, we advance the pointer 1 and decrement pointer 2. Okay? So while this condition holds, while pointer 1 is less than pointer 2, okay, if pointer 1 dereferenced does not equal pointer 2 dereferenced, we're going to return false. Otherwise, we're going to increment pointer 1, meaning move it to the right 1 space, and we're going to decrement pointer 2, which is moving it to the left 1 space. When by the time the loop executes, or the while loop concludes, then we'll return true. Okay? So take a few minutes to look at this code and see if you can figure out what it does. Go ahead and pause the video now. If you thought about it, you could have figured out that the code checks to see if the string is a palindrome. That is, a word that is spelled the same forwards and backwards. We've already talked about the sizeof operator. Can you figure out what the result is when you use the sizeof operator on a double pointer? Again, pause the video and think about it for a couple seconds. You can see that the character is 1 byte, and an int is 4 bytes, and a double is 8 bytes. And our double array is 6 items, so it would be a total size of 48, right? So you can see, let me get laser pointer. So you can see here the size of the array is 48 because our array holds 6 things, right? So 6 times 8 is 48. Now, if you look at the size of the pointer to this array, you'll see that the size is 4 bytes. And we've talked about that because it only holds a memory location. If we change the code a bit, you'll see that the size of the array has changed right here because we have declared it of type int instead of type double, right? But you'll see that the size of it is now 24 bytes because it's half the size of our double array, but our pointer to the array stays the same size. The point of this is to reiterate the difference between a pointer and an array, even though arrays are implemented as pointers behind the scenes. Another question you may be asking yourself is, why do I need pointers if I can just access arrays without the pointers and the funky pointer math? Well, pointers are mostly used to create dynamic variables in dynamic arrays. When we say dynamic, we mean that they are dynamically allocated. This is in contrast to statically allocated variables in arrays we've been using so far. With static allocation, the compiler allocates and deallocates the storage for statically allocated variables automatically. Here's an example of a static allocation. The arrays we've been using so far are statically allocated. For dynamically allocated variables, you, the programmer, handles the memory allocation and deallocation, and it's an awesome responsibility. Here we create a dynamic array of 10 spots using the new operator. The new operator will create a dynamic array of 10 ints by allocating memory space for 10 ints and return the address of the first element of the memory block. So here you can see we've got the keyword new, and we're telling it, hey, I need 10 ints worth of space, and give me the first address of that block. And then we're going to assign it to the pointer right here. This is how we create a dynamic array and let a pointer point to it. Next, we can manipulate the dynamic array using this pointer in the same way we work with statically allocated arrays. So you can see here, we're going to step through for some size from 0 to that size, or well, less than 1. We're going to store some value in that array. So this loop is going to assign 5, 6, and so on to each element of the array, because 0 plus 5 is 5, so we're going to store that in index 0. 1 plus 5 is 6, we're going to store that in index 1, okay, and so on and so forth. After we finish using a dynamic array, we should recycle the memory space by deallocating the array explicitly. We do that by using the delete operator right here. Pay attention to the square brackets between the delete and the pointer p. Okay, this right here is critical. This will make sure that the whole array will be deallocated instead of just one element currently pointed at by P. Again, I got to reiterate, make sure you include the brackets when you delete the array or the pointer that points to that array. Okay? Otherwise, you're just going to delete the first element. Dynamic arrays seem like a lot more effort than statically allocated arrays, so why do we want to use them? Well, a primary reason is when you don't know the size of the array until runtime. If you recall from previous lessons, we had to declare the size of a statically allocated array using a constant integer. This requires that you know the capacity when you write the program, which is often not feasible. Dynamic arrays can be handy for this kind of situation. So this example here shows how you can use a dynamic array to create an array whose size isn't known until runtime. So here we're declaring an integer size, we're asking the user to input how many items they have, and then we're creating this new dynamic array using that size variable using the keyword new. Okay, then we're going to step through all of those items, storing the index in that memory location, right? And then we're just going to print that out. And then when we're all done, we make sure that we're good programmers and we delete the memory allocation by using the delete keyword with the braces to make sure that we are deleting the entire dynamic array. You may recall earlier that we discussed how a Java method can return an array but a C++ function can't. Well, that brings us to our second reason why to use a dynamic array, and that's so we can have a function return a pointer which points to a dynamically allocated array, as illustrated by this function prototype here. Now remember that you also want to have a reference parameter to bring back the size of the dynamic array. So here you can see we are returning a double pointer, right, or a pointer to a double, and here is our reference parameter size that gets passed into this function that we can update with the size of however big our dynamic array is. The C++11 standard adds a convenient way to initialize a dynamic array using an initializer list. This is the same style used for initialization of a statically allocated array, except for we declare it as an int pointer using the keyword new. Note that there is no equal sign or assignment between the list and the array like there is in the static allocation. So here you can see in our static allocation we have this list initializer and we're assigning it to the array. But here in our dynamic array, where we're declaring a pointer to a memory block of size, in this case 5, we are initializing it with those same values, but there is no assignment here because we already have an assignment here, right? So that's just a key difference between the two. So let's look at an example of returning a dynamic array from a function. Pointer PR, which is right here, will receive the address of the dynamic array created and filled in this fill_r function. So here we are going to call this function fill_array, passing in our variable size, and you can see that size has not been initialized to any value, so we're passing it in to get assigned that value when we fill the array, right? And PR is getting assigned to a memory location which is going to point to the array that gets created inside of this fill array. Okay. After we have that memory location, we could now process this array just like we would a regular array. We're going to pass in this, how many elements are inside of it. We're passing a pointer to the array, and then we're just going to print out the contents of it. Then when we're all done, we're going to delete the memory that was allocated by this fill array function. Again, I'm highlighting this because it's critical. Make sure you delete the array when you're done. Now, given the screenshot of one run of this program right here, can you decide which part is from the function fill array and which part is from the print function? Go ahead and pause the screen and think about it. This print from the main part of the program should give you a hint. You can see right here, the standard out, the numbers are, right? So we can look over at our output and see that that function is, or that output is right here. So the lines before that are part of the fill array function. So this is all part of the fill array function right here, right? And the numbers that come after it are part of the print function. So we're doing this because you need to be able to analyze the execution of the results of a program and given a portion of the source code and figure out how the program is organized, okay? Because you're not always going to be giving code that you've worked on, and sometimes you're going to be giving outputs of somebody's code and you're going to be giving their code, and it helps you to be able to figure out what part belongs where. Okay, so we saw the code on how to output the contents of and how to fill it. So let's take a look at how we actually implement the fill array function. We have figured out that the portion before the last line should happen inside of the fill array function. That means we need to first input a size, right? We should then use the size to create a dynamic array before inputting any values. And we need a local pointer variable for that. So here you can see that we are creating our pointer to an array of integers of that size. Now we can input numbers into this array, which requires looping through the number of elements that we are inputting. So from 0 to I, which is less than size, we're going to increment I, and we're going to ask the user to input those numbers. Finally, we need to return this pointer, that is the address of the dynamic array, right? And that's how the main function will be able to get a hold of the contents. So we're just returning the pointer, which remember is only 4 bytes. Now, the only thing we have left to do is to write the function header. Since we know we are returning a dynamic array, we need to specify the return type, which is a pointer to an integer. We know the name because we already used it in the main part of the program, so that's easy. It's fill array. And as we said previously, we are returning the size of the dynamic array that we need as a reference to store it as a parameter. So here you can see we have a reference to an integer, and here we're calling it size, and in the main part of the program we called it size too, but that doesn't have to be the case. So when we update our size here and the user types it in, it's going to get returned to the main programs because the main program is what actually allocated the memory space for that size variable. So that's it. We're done. We've implemented that function. Let's take a quick minute to go back and look at a function that we've been using which involves pointer parameters, just as a refresher. So here we have string copy, where the second parameter is the source C string. And remember, a C string is just a character array. So therefore, it's declared as a const pointer. Here, the const means that the data pointed by the pointer should not change, but the pointer could change to point to other data. So we say that this is a non-const pointer to constant data, right? The character is what's constant, the pointer can change, right? The first parameter is a pointer to the destination C string. And there's no const involved here because this destination, the characters are going to actually change because we're going to be assigning them because we're copying from our source into our destination, okay? So it can be confusing when you start seeing these const keywords mixed in with your parameters, but just remember that this is basically saying our source character array is not going to change inside of this function, and the compiler will enforce that. So let's take a deep dive into the pointer versus references. And I alluded to this earlier, but let's go a little bit deeper so we make sure we have a good understanding of it. Here we have an integer variable called number, right? And you can point a pointer to this int variable, right? So here we have int pointer p number, and we're storing it as the address of number. And this pointer holds the address of the variable number. As you can see here, we have our p number, and it's an integer of type int, and it stores a memory address, which is our address up here for our integer, right? You can access the variable number by dereferencing this pointer. So here you can see that we are dereferencing p number, and here we're printing it out, and here we're assigning 100 to the value that p number points to. If you print out p number, you'll get the address that it is, not the value. The only way you get the value, well, technically the address is the value, but if you wanted the value of the variable that it points to, then you dereference it. So again, it's kind of confusing. This right here, dereferencing it, was we're going to assign the value to the address that it points to, right? Or the variable that is in the address that it points to. We can also declare a reference variable and let it point to an int variable number. So here we're declaring a reference called reference number, and we are assigning it to the number variable, 88. A reference variable also contains a memory address. Okay? However, you can use this reference variable the same way that you use a variable number without any dereferencing. So now look back at the declaration line. We also don't need an address of operator when pointing to this reference to our int variable number. Okay? So here we have a reference called reference number, and we're going to print out this reference number, and that's going to be equal to, in this case, 88, right? Well, actually it's going to be 100 because number is now 100 because we assigned it to 100 right here. If we assign 200, now reference number is equal to 200, which means that number is going to be equal to 200. Now, the big difference here is that our reference variable has a memory location, but we cannot access it directly like we would with a pointer and dereferencing it. Okay, so hopefully that helps bring a little clarity. It probably didn't, but there is a difference between pointers and references and variables. References you can think of as just a simplified pointer because the compiler will handle the dereferencing and all that behind the scenes. So when you declare a reference variable, you just assign it to another variable. You don't have to assign it to the memory of that variable like we do with the pointer here. Okay? So it just kind of handles it behind the scenes. The other difference is once you assign a reference a number, you can't change it. You can't point it to a different variable. So we went through all that to make the case that a reference and a pointer are pretty much equivalent. The only difference is that a reference is a named constant for an address, and you must initialize a reference during declaration. You can't declare it and then later assign it. You also don't need to use the address of operator and dereference operator on a reference, as those are done automatically for you. You can also use a reference the same way you use the original variable that it points to. And so you've been doing this all along with reference parameters when you pass them into functions. So here's why we use references. Number one, it provides us the benefit of a pointer without the syntax complexity. And number two, in C++, we use reference mostly in reference parameters for a function. Now, I found when I was first learning C++ that this actually, dealing with references and pointers, added to confusion because with references, you don't have to use the address of and the dereference, and with pointers, you do. And so I would get confused as to when you use what. So if you get confused with that, don't feel bad. It's normal. But just remember that references are basically pointers that C++ handles the referencing and dereferencing for you. And once you assign it, you can't reassign it. Okay? So it takes away some of the complexity, but adds some restrictions. Overall, pointers, references, and dynamic memory allocation are the most powerful features in the C and C++ language, which allows programmers to directly manipulate memory, the most critical and scarce resource in a computer, for the best performance. Okay, now you might argue that, well, memory is not really scarce anymore, but there are still applications and times where you do need to micromanage your memory allocation. However, the pointer is also the most complex and difficult feature in the C and C++ language to understand and use efficiently and effectively. So don't worry if it takes you a while to get used to the concept, but do allow yourself plenty of extra time to practice and get used to it, okay? Because you're going to have a lot of undefined behavior in your programs when you are using them incorrectly, and your program might compile fine, it's just not going to work as intended, and that can lead to a lot of frustration. So understand that this is a difficult concept to get the hang of, but once you do, it's really not a difficult concept to understand. It just takes practice. Okay? So that brings us to the end of the lesson, where we learned about the meaning of pointer variables and how to use pointers within a program. And again, I'm foot stomping this. This is a complex topic and you're likely to struggle with it at first. So start with small examples until you are comfortable. You should also have learned that a statically allocated array, like the kind that we've been using all along, is implemented as a const pointer. All right. And then finally, we also learn how to use pointers to work with dynamic arrays. And that accounts for pretty much like 90% of the use cases for pointers. So that's it for this lesson. It was a pretty big lesson. There's a lot to unpack with the pointers and the references and the dynamic arrays and all that. So you might want to go back and re-watch it or go through the textbook again. This is a concept that's going to take you some extra time to get the hang of, okay? So that's it for now, and I'll see you in the next lesson.